We're now in a position to start looking at some case studies in the syntax of English and see what finite state models are and aren't able to handle. So I'm going to start off with a fairly specific set of generalizations about English. So first of all, a sentence can consist of the sequence, the words, they are, followed by something that's a noun phrase. You've already seen examples of noun phrases, things like the dog, mice, mud, it, and so forth. Second, a sentence can consist of the sequence, they are gerund verb NP. Gerund verbs include things like jumping, sparkling, sleeping. So for example, they are jumping rope, where NP would be rope. They are flying planes. Furthermore, a noun phrase can consist of a noun preceded by 0 or more adjectives. That is, adjectives can modify nouns. So table is a noun phrase, but precious metals is a noun phrase, big green buildings is a noun phrase, and so forth. And finally, a gerund verb can function as an adjective inside a noun phrase. So for example, sleeping children is an okay noun phrase. Sleeping by itself is a gerund verb, but it can also function as an adjective. So any English word that can serve in the part of speech gerund verb can also serve in the part of speech adjective. So before I go on, I want to recommend an exercise for you, which is to try to express these generalizations in a finite state model for the fragment of English syntax over the alphabet that consists of the words they, are, gerund, and then word categories, gerund, verb, adjective, and noun. So you can go ahead and pause the lecture and go ahead and do that. Take as long as you want. You back? Okay, great. Here we go. Here is an example of a finite state model that you might use to express these generalizations. Okay, so this is very simple. If we look at a couple of paths through the automaton, there's they are gerund verb noun. So once again, so for example, they are flying planes, where flying would be the act of flying as an example. But there are other paths through this automaton. So for example, they are planes. And furthermore, they are green trees, and so forth. Now, this implicitly captures a bit of syntax not only in the word sequences that it accepts and rejects, but actually in the structure of the automaton in an interesting way. I made reference to the idea of a noun phrase in my generalizations. Now the word noun phrase, like nothing explicitly is marked in this automaton that has anything to do with noun phrase, but you can sort of conceptually see that there's sort of a dividing line here, that everything that is after this point, once you get to state 4, you're inside this noun phrase that is after the verb, whether it's are or are plus a gerund verb, and everything beforehand is outside of the noun phrase. Okay, so this getting to Q4, that's state number 4, is sort of a dividing line in the syntax, but that's not explicitly represented, but it's there. It's a resource that we can sort of think of as a way of describing a difference in the parts of structure of this string. And if that's not satisfying enough, note that we could make this more explicit by converting the automaton into a finite state transducer and having annotations of the phrase boundary, the beginning of this noun phrase, be actually represented in the output. So if I created the transduction side, the output alphabet that included all the things that I've added on in green, so now this it still matches these inputs. They are verb gerund noun and they are adj noun, but it would annotate this additional output token beginning of a noun phrase in different places. It would annotate it after the gerund verb, but before the adjective. So that's one way you could sort of think of getting some structural characterization into an automaton. The broader point here, though, is not whether this particular structural characterization is right or not. It's that the automaton, the paths through the automaton, which we haven't actually sort of thought of as explicitly having any role in our theory of language, might be a resource that we can use to describe and distinguish between different ways of generating or interpreting a sequence of symbols. And so the multiple paths through this automaton offer the possibility for different structural descriptions. This is the launching point for what I want to describe as an important distinction in the theory of natural language grammar, which has played an important role throughout the history of cognitive science, and is the notion of the distinction between weak versus strong generative capacity. So generative capacity is what a formal device can generate or license as a set of objects, where we're mathematically treating objects as instances of the sort of the system, the representational system that we're interested in. In our case, it's language. For example, if we're looking at sentences, we're interested in grammatical objects, syntactic objects. So the weak generative capacity of a device or grammatical formalism is what languages as string sets, as we looked at in formal language theory already, can be defined by a grammatical formalism. And so these examples of where the tokens, the actual string elements, are just these things that have their words or maybe parts of speech, is an example of something that we can talk about with weak generative capacity. We can contrast this with something a little bit different, which is strong generative capacity, which is the idea there is that you're not just interested in strings, you're actually interested in some additional content that lives on the strings. And we call those structural descriptions. And this is central to the theory of language for a wide variety of approaches, including generative grammar, many different alternative approaches to grammar, and a whole bunch of tools and mechanisms and approaches in natural language processing as well. So here we might not just want to say, well, the grammar licenses just the word sequences or the part of speech sequences, but also says that if the part of speech sequence is going to be generated, there's some structural bits to it. For example, the beginning and end of the noun phrase, and there may be any of a number of these. Okay, so if we just sort of go back and we think about what is this model capturing or failing to capture, we see that from the last slide that finite state machines both offered a characterization of the a weak generative capacity characterization of this gerund adjective ambiguity, but also a strong generative capacity characterization, because they could mark the onset of the boundary of that noun phrase in the right way, depending on what the part of speech of the incoming word was. Okay, so that's case study number 1. Here's a second case study, multiple prepositional phrases in English. So I'm going to give you a different set of generalizations here. First, a noun phrase can consist of a determiner and a noun optionally followed by one or more prepositional phrases. Second, a prepositional phrase consists of a preposition followed by a noun phrase. And examples of these would be things like a joke about the woman with an umbrella, a joke about the woman with an umbrella on the street, and so forth. I could add as many prepositional phrases as I wanted. Now, you'll notice that the meaning starts to get more and more complicated, but that's not the only thing I want you to notice. I want you to think carefully about what's going on here. And once again, I would like you to start by take a moment and try writing a finite state automaton for describing this. And you can see this will be an infinite series of noun phrases of this form. So first, do that. Come back when you're ready. I'll be waiting. Okay, you ready? Here we go. So what I want you to observe is that as the prepositional phrases accumulate, the meanings multiply. So let's consider the first case where I'm just going to actually get rid of with the woman on the street, with an umbrella on the street, and I'll just think about the phrase, a joke about the woman. If I think about what the phrase about the woman is doing, there's sort of really only one thing that it's doing. It's modifying a joke. Okay, it's saying what kind of joke is it. But let's say that I add, now I'm going to just keep on the street away, but I'm going to leave with an umbrella on. So now it's a joke about the woman with an umbrella. Now, you probably have one meaning that comes to mind, but actually what I want to draw your attention to is that there are multiple possible meanings for this phrase, for this noun phrase. And I will illustrate them informally in the following way. I'll take the with an umbrella phrase, and I'll note that it can actually point to it can modify semantically either a joke or woman. And this corresponds to the difference in interpretation of, does the woman have the umbrella? Or does the joke involve the umbrella but the woman doesn't necessarily have it? If the woman has the umbrella necessarily, then I would say that is this interpretation up here that I have, and I've illustrated this with a little arrow in purple that points from with to woman. And that's actually a kind of what's sort of a dependency relationship, which actually has some formal uses that we may encounter later on. Alternatively, with the woman with an umbrella might be maybe the umbrella's in the joke, but the woman doesn't possess it. So it's like a joke with an umbrella involved. And there I would use the green line, which connects with directly to woman and skips directly to joke and skips over woman. Okay, so that's with on the street, right? Or missing. What about when I add on the street? So now it turns out that there are, in both the case where with modifies woman and with modifies joke, I can accommodate on the street in different ways, and there's actually multiple ways for either of those interpretations to be brought together. And I illustrate them with the dotted lines here. So on the street, if with modifies woman, then on the street might modify an umbrella, so the umbrella's on the street. The woman might be with the umbrella and the woman might be on the street, where on the street would modify woman. Alternatively, maybe the joke takes place on the street, and actually on the street is not saying where the woman is at all. If with an umbrella is modifying joke, it turns out, and I recommend that you think about this for a while yourself, offline, it turns out that the interpretation where on the street modifies woman is not available, but the other two interpretations where it modifies umbrella or modifies joke is available. So there are actually 5 different interpretations here, 3 on the top and 2 on the bottom. Okay, and so actually it turns out that the number of meanings turns out to grow as the Catalan numbers, which is a very, very fast, it's an exponential increase. So this is a challenge. We've observed empirically that a noun phrase can consist of a determiner and a noun, optionally followed by one or more prepositional phrases. And furthermore, we see this prepositional phrase, we say it's a preposition followed by a noun phrase, infinite sequence of prepositional phrases. What about a finite state model? So I asked you to try doing this. This is one that you might try. This is a very simple model. It just actually has these 3 states, and it allows you to generate determiner noun. You can loop through it once and generate determiner noun preposition, determiner noun. You can loop through it twice and you'll get determiner noun preposition, determiner noun preposition, determiner noun, and so forth. You can loop through it as many times as you want. So it actually will accommodate any of these for an unbounded number of prepositional phrases. However, you noticed in terms of the meaning, it's obvious that there are different ways of associating these words with each other that lead to different meanings. And ideally, we would like our formal apparatus for describing the language to capture those kinds of differences in meaning. And as you can see, if we're trying to use paths through the automaton or anything like that, there's no method that the automaton gives us, that this particular automaton gives us, to do that, because there's only one path through the automaton for no matter how many prepositional phrases there are. And you can imagine adding states to change this. So for example, if I have two of these, and suppose that I have a joke about the woman with an umbrella. So now I could, for example, here's one path that I could take, and here is a second path that I could take. And these would be 2 different paths, and maybe I would want to somehow identify these through some transduction annotations with the 2 different interpretations about does the woman have the umbrella, or is it just the umbrella and the joke and the woman doesn't have it? But you can see that every time I add a prepositional phrase on, I would need to create more and more of these options. So if I were to go to 3, well, I showed you that there are 5 different interpretations, and if you look carefully at this, if there are 3 prepositional phrases, there are only going to be 4 paths. And because the Catalan numbers grow too fast for you to sort of set a finite number of, there will always be a maximum number of paths, and since the Catalan numbers grow in an unbounded way, no matter how many states you add, there will always be a long enough sequence of prepositional phrases following a noun phrase that it's too many. So we'd have to instead add states for every additional level of prepositional phrase stacking, but then we don't have a finite model anymore that allows us to accommodate an infinite series of phrases of increasing complexity. So this shows that whereas in the previous case we had a finite state model that was able to both give a weak and a strong generative capacity account of a phenomenon, the gerund and adjective ambiguity. In this case, noun phrases with stacked post modifiers, their prepositional phrases, have an interesting status. Finite state machines have the weak generative capacity to accommodate these, but they do not have the strong generative capacity to offer all the necessary structural descriptions. So this is an example where weak and strong generative capacity are pulled apart for a particular case of models.